Hi everybody. So in this video, we're going to look at using the central limit theorem with a Poisson binomial and geometric model. So we'll work through these three examples, and if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So in this example, we're told that a call center receives an average of 15 calls per hour, and the number of calls received per hour is modeled with a Poisson distribution using this model here. And a manager records the number of calls received over a random sample of 40 hours. Using the central limit theorem, approximate the probability that the average number of calls received per hour over a 40-hour sample is greater than 16. So we know in a Poisson model, the mean is the same as the variance. So the variance of x should be approximately 15 as well. So we can define our sample mean, x bar, as being distributed normally with a mean of 15, this is taken from this Poisson model, and a variance of 15 over the sample size, and we're told that the random sample of 40 hours, so the sample size is 40. So this is our normal distribution for the sample mean, and we've been asked to work out the probability of the sample mean being greater than 16. So this is where x bar is greater than 16, okay? So if I sketch this as a diagram, we've been told that the mean is 15, and we want the sample mean to be greater than 16. So I'll label this here, and we want this region. So if we go to our calculators, we'll choose home, and we want distribution. Then we want the normal CD. The lower is for 16. The upper has to be 3 standard deviations above the mean, or any value bigger than that. So I'm going to enter 100. The mean is 15, and the standard deviation is the square root of variance, which is 15 divided by 40. We'll execute that, and we're told that the probability of the sample mean being greater than 16 is 0.0512 to 4dp. Okay? In the next question, we're going to look at using a binomial model. So now we're told that a quality control inspector checks a factory's production of a small electronic components, and the random variable y is distributed binomially with 500 trials and a probability of success of 0.62, and y represents the number of defect-free components produced per day. We're told that a random sample of 120 days is taken, and then we've been asked to estimate the probability that the mean number of defect-free components per day is less than 308. So perhaps you want to try this question yourself. You'll need to work out the mean and the variance of a binomial distribution. Okay, so how did you get on? Well, we know the mean, or the expected value, of a binomial distribution is the number of trials, n, multiplied by the probability of success, p. So in this case, it will be 500 multiplied by 0.62, and this will be 310. So this will be the mean for our sample mean distribution. And the variance will be n times p times 1 minus p. So this will be 310 multiplied by the 0.28. And we can work this out, and we get 86.8. This is our variance. So now we can define our sample mean distribution. Y bar will be distributed normally with a mean of 310 and a variance of 86.8 divided by our sample size of 120. And we've been asked to work out the probability that the mean is less than 308. So a probability that Y bar is less than 308. And I'm going to sketch the normal distribution curve. So we've got our mean as 310, and we want to look at the region which is less than 308, so this region here. So if we go back to our calculators, now I'm going to define the lower as 3 standard deviations below 310, so I'll just choose 0. The upper, you can see, is this 308. The mean is now 310. That's the square root of 86.8 divided by 120. And this will give us a probability of 0.009. Okay? So this is the probability of having a sample mean less than 308. Let's try one more question. So now we're told that a factory produces electronic components and each component is tested for defects. The probability that a component passes the quality test is 0.3, and the number of components tested before the first pass follows a geometric distribution. A quality control inspector records the number of tests required before the first pass over a random sample of 50 batches, and using the central limit theorem, approximate the probability that the average number of tests before the first pass is greater than 4. So perhaps you want to try this question yourself. You can pause the video and come back when you're ready. Okay, so welcome back. So we need to work out the mean of this distribution. And this is the expected value of our geometric distribution, which is 1 over p. So this will be 1 over 0.3, which is 10/3. And then we need to work out the variance. This will be 1 minus p over p squared. So 0.7 over 0.3 squared. And this gives us 70 over 9. So now we can define the normal distribution from a sample mean. This will have an average of 10/3 and a variance of 70 over 9 divided by 50. And we want the probability of that sample mean being greater than 4. So I'll sketch the normal distribution curve. We've got our mean as 10/3, and we want the probability of the sample mean being bigger than 4, so in this region. So we'll go back to our calculators. The lower is now 4. The upper is anything 3 standard deviations above the mean, so I'm going to leave that as 308. The mean is 10/3, and the standard deviation is 70 divided by 9 divided by 50. And that will give us a probability of 0.0455. Okay? Well, thank you very much for watching. I hope that's given you an idea on how we can use the central limit theorem with discrete distributions. If you found that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.